Morning students, today I will determine the electric potential due to a system of charges. In our previous lecture, we have calculated the electric potential due to a point charge. Today, suppose you have a system which consists of more than one charges. Suppose it had n charges in general. This is a charge Q1. This is a charge Q2, this is a charge Q3, and likewise this is a charge Qn. Now this is the point where the electric potential due to this system of n charges has to be calculated. Here let R1 is the distance of this charge from the point P where the potential has to be calculated. This is R1. This is R2. R2 is the distance of charge Q2 from the point P, and this is Rn. Rn is the distance of nth charge of the system from the point where the potential has to be calculated. In our previous lecture, we have derived the expression for the electric potential as V is equal to 1 upon 4 pi epsilon naught Q divided by R. It means that potential depends directly on the charge and inversely on the distance. So in place of Q, you have now n charges Q1, Q2, Q3, Qn. So for those charges, the potential will be V1 is equal to 1 upon 4 pi epsilon naught Q1, and its distance is R1. Here R1 is the distance, as you can see in this diagram. What is V2? V2 is the electric potential due to the charge Q2 at this point P. So it can be written as 1 upon 4 pi epsilon naught Q2 upon R2. And likewise, for nth charge, the potential will be how much? Vn is equal to 1 upon 4 pi epsilon naught Qn upon Rn. Rn is the distance of this nth charge from the point P. Now, I am supposed to find the potential of the system. So, as you know, that the potential is a scalar quantity, so it can be added by the simple method of algebra. No vector is there. Potential is not a vector quantity. Had potential been a vector quantity, then we cannot add them all by the simple law of algebra. There we would have used the principle of vector addition, that is by parallelogram law or the triangle law of vector addition. But here potential is not a scalar quantity. Please keep in mind, potential is a scalar quantity, so it can be added by the simple law of algebra. Like how you add 2, 3, 4, these are numbers, scalar quantities. So the net potential, total potential at the point P due to all the n charges will be the algebraic sum of V1, V2 and Vn. Now, in all the terms V1, V2, Vn, I have 1 upon 4 pi epsilon naught common. So I will write it as, I will take 1 upon 4 pi epsilon naught common from all the terms, and what is left here? Q1 by R1 plus Q2 by R2 and Qn upon Rn. Right? Now 1 upon 4 pi epsilon naught is 0. So this term, all these terms under bracket can be represented in generalized form as summation Qi upon Ri. And what are the values of I? How I varies in this summation? I varies from 1 to n, because I have a system which consists of n charges. If I put I is equal to 1, then what will come here? Q1 upon R1. This will give the first term in your this equation, If I put I is equal to 2, then Q2 by R2 will come, and this will represent the second term. And likewise, when we put I is equal to N, then Qn by Rn comes, which represents this term, last term, the potential due to the nth charge of the system. So the electric potential now due to a system of n charges can be written as I is equal to 1 to n summation over Qi by Ri. This is the generalized expression for the electric potential due to a system of n charges.